Good morning. Welcome to this session. Alexei, good morning.
Good morning.
Yes, we'll be your presentation, hybrid radio frequency, free space optical radio frequency multi-hop relay, performance in presence of hyper-relic fading. So, Alexei, you can start whenever you have.
Thank you. Do you see my slides now?
Yes.
Yes, thank you. Good morning. My name is Alexei Kvaterek, and I represent Yaroslavl State University with the entitled research, which specifically studies hybrid radio frequency and free space optical communications with multi-hop relays in presence of severe hyper-Rayleigh fading. Nowadays, the increasing demands for high data rates in crowded radio spectrum is pushing modern wireless communications technologies towards hybrid solutions. For example, among such hybrid solutions, one can mention radio frequency and free space optical communication systems, which combine radio frequency link for robustness and free space optical links for high bandwidth. Their application can sufficiently extend coverage, especially in non-line of sight conditions. Thus, towards nowadays, there are many ongoing research projects analyzing possible applications of such hybrid systems in various areas. For example, device-to-device communications, underwater optic communication, unmanned aerial vehicle communication, reconfigurable intelligence surfaces, and industrial IoT, and many other areas. However, these systems face severe challenges from turbulence in optic link, and what is more interesting for our research, severe fading and shadowing conditions in radio frequency segment. The latter ones can be efficiently described in terms of the so-called hyper-Rayleigh conditions or hyper-Rayleigh regimes, which describes fading severity compared to standard Rayleigh, which is more severe than standard Rayleigh fading. Our research provides analytical and numerical results for designing resilient communication systems under these worst-case scenarios, ensuring reliability. Let us assume a relay-based wireless communication system with 3 hops, with 2 radio frequency links and 1 free space optical communication link in the intermediate. Let's further assume that the relays function in amplify and forward mode with available channel state information. And in order to study with the worst-case conditions, we'll assume that radio frequency segments are impaired by fading that are sufficiently heavier than predicted by a standard Rayleigh model. In this case, it is clear that the total signal-to-noise ratio at the output of the system will be defined in terms of the signal-to-noise ratios in each of the segment, and thus will be heavily impaired by the channel fading models. And since we are mainly interested in worst-case propagation scenarios in radio frequency segments, we'll choose these models accordingly. As it was mentioned, in order to describe the severity of propagation conditions, we use the concept of so-called hyper-Rayleigh regimes. This framework classifies all the fading severity compared to the standard Rayleigh fading in terms of amount of fading, asymptotic outage probability, and asymptotic ergodic capacity. The channel can be in full hyper-Rayleigh, strong hyper-Rayleigh, weak hyper-Rayleigh, or no hyper-Rayleigh regime, depending on how many conditions are satisfied. To describe such fading conditions, we adopt the inverse power Lomax channel model in both radio frequency segments. It is a 3-parametric distribution with a signal-to-noise ratio and 2 shape and form parameters and scale parameters, alpha R and beta R, which control the form of the distribution curve. The convenience of this model is in the fact that it can analytically be tuned to operate in any of the hyper-Rayleigh regimes. To prove this, the hyper-Rayleigh conditions implied on amount of fading, asymptotic outage probability, and asymptotic ergodic capacity were derived. Although the results could not be explicitly evaluated but the exact boundaries separating the specific hyperrelay regimes can be evaluated numerically, and the parameters corresponding to each of the hyperrelay regimes can be extracted numerically, what we further did. For free space optical communication link, in our research, we selected a well-renowned Malaga model, which accurately captures atmospheric turbulence effects. This model is a powerful tool because it provides a uniform framework that accounts for all significant components in the optical signal. Those are the direct line of sight component, the scattered line that is aligned with the line of sight component, and the scattered line that is not aligned with line of sight component. The model parameters such as alpha f and beta f allows us to simulate a wide range of turbulence conditions. To assess the performance of such wireless communication system, it is a common practice to describe it in terms of various performance metrics, including the reliability metric. For example, here we use the outage probability as the probability that the signal-to-noise ratio, instantaneous signal-to-noise ratio, falls below some predefined threshold, and the quality metric. Here we use average bit error rate. Although it is well known that there is no single metric that can solemnly define the performance of a wireless communication system, but as we see, both those metrics depend on the average signal-to-noise ratio, so we can link those two into one metric, which can simultaneously help to describe both reliability and quality. And this joint analysis can help us to understand the fundamental trade-offs between links reliability and communication quality. Due to intricate combination of channel parameters and channel models, for further analysis, we resort to numerical approach with the solution setup given in the presented tables. It should be pointed out that we specifically include two turbulence regimes, weak turbulence for relatively clear air and moderate turbulence as might be expected in hot and unstable environments. And the radio frequency link parameters were chosen in such a way to cover full hyperrelay and no hyperrelay regimes. Those are the two extreme regimes. We'll start with a separate analysis of the outage probability and error rate as functions of average signal-to-noise ratio. Here we have double-axis plots for two cases. When the signal-to-noise ratio is varied in all the channels, it is the figure on the right, and when it is varied only in one or two segments, and in other segments it is fixed. This is a plot on the left. Since the total signal-to-noise ratio can be approximated as the minimum of signal-to-noise ratios in all the links, this leads to a threshold effect and for both reliability and quality metrics. Thus, for further analysis, we'll assume the first case when the signal-to-noise ratio simultaneously changes in all the channels. And one can see that for high signal-to-noise ratios, the quality metrics and reliability metrics perform similarly. And this is not so in the small signal-to-noise ratio regime, where the reliability can be a little bit higher than quality, or vice versa. Here we have an example of such curves, joint curves for 16 QAM modulation with a variable threshold outage. And the key takeaway in this trade-off is the trade-off between the two. A low threshold like -10 dB gives us high reliability but poor quality. For example, for target rate, average bit error rate of 10 to the power -3, the best reliability you can achieve is about 0.9 times 10 to the power -3, and it requires quite high threshold for 10 dB. This shows how the system can be tuned based on whether your application prioritizes never dropping the connection or having few errors when it is connected. We can reverse this analysis for a fixed threshold of 0 dB and varied modulation order. The obtained results demonstrate that high order modulations, like for example here 1024 QIM, drastically increase the error rate for a given level of reliability. Moving from 16 QM to 256 QM increases the average bit error rate by a full order of magnitude, which is quite high in practical applications. This directly informs adaptive modulation strategies. For example, use robust low-order modulations like 4QM when the channel is poor, or switch to spectrally efficient like 256 QIM when the highest snare when the signal-to-noise ratio is quite high. The previous results were obtained specifically for weak turbulence and only weak hyper-Rayleigh regime. Here we have the combined impact of radio frequency fading severity. Here we have two regimes, full hyper-Rayleigh regime for small alpha and no hyper-Rayleigh regime for large alpha, and two optical turbulence models, weak turbulence and moderate turbulence. We see that with the favorable radio frequency conditions, those are large alphas. The system is very sensitive to optical turbulence. However, in full hyper-Rayleigh regime, those are coincided black and blue curves. The turbulence, the optical turbulence does not impact at any state. This is a critical insight for designing such systems. For example, when the radio frequency fading radio frequency link experiences severe fading, the optical turbulence becomes a secondary concern and can be regarded while optimizing such a system. Which means that the system's performance bottleneck is entirely in radio frequency segment. And summarizing the above and concluding the performed analysis, I'd like to give some general closing remarks. First, our research demonstrates the full hyper-Rayleigh, the impact of a full hyper-Rayleigh regime in radio frequency links and the requirements that it imposes to synthesis of such systems. Second, we noted that multi-hop architectures suffer from cumulative distortion, and it is critically vulnerable to asymmetric conditions where the weakest link dominates overall performance. And third, to combat these adaptive strategies are not optional but essential. This includes dynamic modulation, switching, for example, from 4QAM in poor conditions to higher QAM orders when the fading conditions in radio frequency link are quite good, and implementing threshold-based power control. It must be highlighted that our research can be of special interest for relay-based assisted communications, which are highly susceptible to radio frequency link, when the radio frequency link is highly susceptible to dynamic blockages and severe fading from buildings, for example, or vehicles, which corresponds to full hyper-Rayleigh regimes. For example, like 5G and 6G network backhauls, like relay-based industrial, IoT, and smart factories. Thank you for your attention. I'll be glad to answer questions.
Thank you very much, Alexei. So anybody have any questions, doubts, something? Well, Alexei, I have some questions. Well, actually, it's only one. It came to my mind when you put the probability of outage. That this probability of outage is when the signal goes below the threshold level. And this is, well, I think this would be for the continuous channel when we have just modulation. But when we have the influence of coding, we might need the probability that those crossings have certain duration of time.
You are perfectly correct. This is the so-called second-order statistics when you need to fading duration and average crossing rate, fading statistics. Those are, we are up to now studying those effects. Those are separate, like first-order description, second-order description, a little bit more complicated, but we are in process up to now. But you are perfectly correct. This is a very important topic for reliability.
Yes, and my question was because I saw that for the probability of outage, you need really very, very strong signal to noise ratio in order to get very small probability of outage because it is this heavy tail fading conditions. And my question was, I was wondering when you might include the influence of the coding, how do you expect that this probability of outage would be? You will require more signal to noise ratio or less signal to noise ratio?
Our preliminary studies demonstrate that we need exactly a little bit more signal to noise ratio, and thus, and at the same time, we would like to maintain high reliability, not only high quality. So we need to maintain quite low threshold signal to noise ratio. So this is quite an interesting problem to find a compromise between the two. So keeping up some quite low threshold signal to noise ratio, and at the same time keeping a little bit higher average signal to noise ratio to achieve the required error rates.
Okay, thank you very much. Somebody else? Well, Alexei, hold on because you will be the third exposition.
Thank you very much.
Well, now the second talk will be signal to noise ratio enhancement in orthogonal frequency division multiplex systems, non-linear filtering approach, and I will be talking about this topic. Well, my name is Fernando, and I will be in charge of explaining you what all this means. When we say non-linear filtering approach, tengo que cambiarle. Perfect. Actually, it's the short name for what it is called multi-moment house-based extended Kalman filtering. So whichever you prefer, the long or the short version, this is what you will be hearing right now. Well, when we have communication signals for phenomena, we usually take Markov processes or stochastic differential equations in order to model those signals and phenomena in telecommunication. When those signals are under the influence of additive white Gaussian noise, we want to filter this influence. And for the filtering, we take a Bayesian approach. And as you might know, when we have Bayesian approach, we need the a priori information. For the a priori information, we mean the a priori probability density function of the signals we are studying. The a priori probability density function is given by the Fokker-Planck Kolmogorov equation shown here. That's the first requirement. As a second requirement, we need the a posteriori information. The a posteriori information is after we have the influence of our noise, we want to see how the probability density function changed. So the a posteriori probability density function is given by the Stratonovich-Kushner equation, which is shown here. And we have everything to solve this filtering problem. There are several solutions for this filtering problem. And the solution that it is interesting for us is the solution that it is based on the Kalman filter. However, for the modeling of orthogonal frequency division signals, we found that the Markov processes and stochastic differential equations are not adequate. We found that chaotic strange attractors are useful to make the modeling of these signals. And this was made not only for OFDM signals, we found this for radio frequency interference signals, for fetal electrocardiograms, for voice-like signals. So Markov processes and stochastic differential equations are not adequate to make this modeling. So these are the nonlinear equations for the chaotic strange attractors, and we have a continuous form and discrete time representation. We use the discrete time representation because for the modeling, we can adjust the sampling time of these equations and adjust our modeling. So those equations for Rosler, Lores, and Chua, we see that they are three-dimensional. They have different components, and each component has different dynamics. The Z component is impulsive, so it can be used to model impulsive phenomena. The other components, X, Y, and Z, for Rosler, Lores, and Chua, are oscillatory in nature. So it is adequate to use those oscillations to model OFDM signals. So we found in our work that Rosler with X component is adequate to make the modeling of those signals. But those are deterministic equations, and we are trying to model stochastic phenomena. So it is not possible to do that. The solution is that when we include some noise, we make addition of some noise to the system of equations. And if the noise has very, very small intensity, we can transform these ordinary differential equations into stochastic differential equations. So as we have Gauss stochastic differential equation system right now, then we can apply the filtering methodology that I already described. The difference here is that we're using nonlinear equations. So instead of the Kalman filter, we use the extended Kalman filter, which allows us to make the filtering. But all this filtering is taken for one moment of time. We take one sample and make the processing. Then another time, the sample and processing. So it feels more natural to take several time instances for this modeling. So when we take several time instances, we need the a posteriori probability density function for the multi-moment case. So it means the multi-moment Stratonovich-Kushner equation, which we see allows here to incorporate through partial derivatives different moments of time. But this is the formal approach. The solution for those multiple partial derivatives is somehow rather complex. So we found that practical solutions can be found when we take only 2 moments of time. When we take only 2 moments of time, we can get suboptimal solution for this filtering problem, which is also based on the extended Kalman filter, but for 2 moment case. So 2 moments of time, 2 samples at the same time for filtering. So how this 1 moment and 2 moment extended Kalman filter works? Well, we have 2 cycles, prediction and correction. In the prediction, we make a prediction of what the next state, the next sample would be. We make also a prediction of the error covariance matrix. What would be the error of this filtering? In the correction cycle, we make an update of our prediction by using the Kalman gate, which allows to make ponderation between the signal we measure together with noise and the value we expect. So we make an update, and also we make an update of the error covariance matrix, and the cycles starts to go for the next sample and so on and so on. For the 2 moment extended Kalman filter, we have the same, the Kalman filter, but there is a small difference. We have this term here, which is the error covariance matrix with a new factor where that allows to introduce the correlation coefficient, which means that when the correlation is 0, the samples are very separated. So it is 0, this is 1, and we have only 1 moment filtering, which is the same. But when the samples are close, this correlation coefficient starts to grow. So it's 1 minus this correlation coefficient. So this is a very small quantity and makes this error covariation matrix to get decreased. So we have an improvement for the filtering because we're taking into account 2 samples. The system we're considering is single input, single output channel with quantum constellations. And for the OFDM, we have 512-point fast Fourier transform, a cyclic prefix length of 8, and we make an oversampling in order to make smooth the signal. Our signal has to be smooth. But nothing comes for free. We need to fulfill 3 conditions for this modeling to be useful. First condition is time scale. As I said, we are using chaotic equations to model. stochastic signals. So the time scale has to be comparable. So we have the OFDM signal and the Rosner X component. So by adjusting the time sample, the sample time of the chaotic equations, we see that the dynamics are somehow similar. So this is the first level complete. Second level, we need first order approximation. So the probability density functions have to be also adjusted. Here we use the statistical goodness of fit test, Kolmogorov, Smirnov, and chi-square. And those tests have sensitivity, different sensitivity for different regions of the probability density function. We see that with 90% or more confidence, we can say that those probability density functions have a match, a good match. So second level, complete. Third level, we need second order statistical match, so the autocorrelation. For the autocorrelation, as we are using two-moment approach, the samples are going to be rather close. So for the autocorrelation match, we're interested in the main body of the autocorrelation because the samples would be rather close to each other. So it is important only in this region. So the statistical analysis shows that the mean square error, 0.17, which is rather good. And so we have the third level complete. So we're ready to apply this modeling and see how it allows to improve the signal to noise ratio. Here we have the original signal, and after we apply the first moment filtering, we have less noise. So we get an improvement here, an improvement regarding the original signal to noise ratio. Second moment filtering gets an improved accuracy. So we have further improvement of the signal to noise ratio. However, this filtering has to be robust for all the parameters that have influence. So we want to see how robust this filtering is. Here we show that first of all, when we have the parameter signal to noise ratio, when we have signal to noise ratio bigger here, we don't have any improvement, and we don't need it because the signal is very strong. But when we have signal to noise ratio rather small, the noise is very heavy. So here we have the area of opportunity for filtering. When we apply first moment, we have this gain, and second moment allows even additional improvement. We want to see how robust is this filtering for the different quantum constellations. So when we have 256, we have this boundary. The constellation size bigger than this get the same curve. So this is the boundary. We see that from here to here, we get a reduction of the signal to noise ratio gain. Why? Because the constellation is rather overcrowded. However, it is stable here. In order to get some benchmarks, we use the Kalman filter, which is the base for extended Kalman filter, and the Wiener filter, which is the most basic filtering strategy. We see that here are our benchmarks, and the nonlinear filtering provides, of course, a gain. But remember that we have this Q value, which is the process noise in the Kalman filtering. And this process noise is responsible precisely for transforming the ordinary differential equation to stochastic differential equation. So we want to see how robust it is in relation to this. When we have this process noise value here, we have this boundary. When we increase this process noise, our modeling is extremely noisy. So it is not an adequate modeling. So the filtering is not useful. So we have this boundary here. When we reduce the process noise up to this boundary, we stay here. When we have even further reduction of this boundary, the noise is very small. So we don't have stochastic differential equation. We have ordinary differential equation, which is not an adequate modeling, and the filtering is no longer useful. But it is stable in this region. Finally, we want to see the influence of the fast Fourier transform for the OFDM signals. So we fix the quantum constellation size. We fix the process noise intensity here. And we see we have two boundaries here for the fast Fourier transform size. When we have the fast Fourier transform sizes lower than this, we get the same curve. We increase the fast Fourier transform size to this value, and we get this boundary. Fast Fourier transform sizes bigger than this get the same curve. So, in conclusion, the nonlinear filtering approach based on multi-moment Gauss-based extended Kalman filtering, it is robust on the different parameters, on the different constellation sizes, on the different fast Fourier transform for the OFDM signals, and on the different process noise, which allows stochastic differential equations model. So, thank you very much. If you have any questions, please feel free to ask.
You mentioned that you can apply this method only for 2 months of time to samples.
Yeah.
Why? Why could you do that?
Yes, I can explain why for only 2 moments. Actually, I said several moments of time. Here, in the Stratonovich-Kuchner equation, we have partial differential equations that account for different moments of time. When you're trying to solve analytical closed form for this, actually it's impossible because you have a lot of moments of time. But when you take only 2 moments of time, you are somehow in the asymptotic condition, and you can get analytic closed form solution. That's why it is. And we need those analytical form closed solutions in order to have the equations for the filter. That's why it is only with 2 moments of time, practical solution. So, thank you very much. And we go to the next talk. Sergey, are you there?
Yes, of course.
Okay, we are ready for the second talk.
Second presentation.
A strictly positive secrecy capacity analysis of a wiretap wireless communication system in presence of full hyper-radial fading channel. So go ahead.
Oh, thank you very much. Nowadays, the evolution of modern wireless communications towards 6G and Internet of Everything promises like millions and requires millions of low complexity and energy constrained devices. For these devices, traditional ciphering is often too computational complex, and this is where the physical layer security methods become crucial. The physical layer security exploits the inherent randomness of the channel, of the wireless channel, and guarantees the secrecy at the same time. However, a major challenge arises in harsh urban environments with poor propagation conditions where the signals experience heavy fading. Most classical models like Rayleigh model, Rayleigh models, Nakagami, Hoyt model fading do not fully capture the severity of these conditions, and it is where the hyper-Rayleigh fading regimes methodology can be efficiently applied. It describes the channel that are significantly more severe in fading conditions than predicted by the classical Rayleigh model. Our work focuses on the most severe class, the full hyper-Rayleigh regime. The urgency of this topic lies in ensuring that future massive and low-power network remains secure even under the most pessimistic channel conditions. For this, we assume a classical wiretap communication model proposed by Weiner in his classical work. In this case, a message block X, W encoded by the source code and channel coders called Alice into code word X, which is passed through a main channel to a legitimate recipient called Bob, whose estimates by some means are transmitted, who estimates the transmitted signal by some means. And the transmitted signal is sensed by the eavesdropper called Eve through a wiretap channel. Both channels are characterized by the additive white Gaussian noise and by fading and shadowing that is represented with the channel coefficient H, which can be recalculated into the signal-to-noise ratio gamma. We'll denote the variables corresponding to the direct channel and eavesdropper channel with the substrings D and E respectively. As it was stated earlier, in order to analyze the severity of fading, we use the methodology of hyper-Rayleigh regimes or hyper-Rayleigh fading. This I will a little bit tell again about it. It describes the severity of fading in terms of amount of fading, asymptotic outage probability, and asymptotic ergodic capacity. And it classifies all the fading regimes depending on how many conditions are met into full hyper-Rayleigh, strong, weak, and no hyper-Rayleigh regimes. In our research, we are mainly interested in a more severe full hyper-Rayleigh regime. And to model such fading, we use the Lomax distribution, which is a two-parametric model described by a shape parameter alpha and average signal-to-noise ratio. The strong points of this model are, first, its mathematical tractability, and second, its capability of describing severe fading conditions, because it belongs to the family of the so-called heavy tail distributions. Moreover, it was proved to be always in full hyper-Rayleigh regime, irrespective of the parameter. This makes it a perfect model for our worst-case secrecy analysis. To quantify the performance of the described system, we'll assume such a metric as the probability of strictly positive secrecy capacity, which defines whether the secure communication is possible at all. It is a specific case of a more general physical layer security metric, the secrecy outage probability, which defines that the probability of the instantaneous capacity falls below some pre-specified target rate. Following some mathematical procedures, the closed form expression for the secrecy outage probability and strictly positive secrecy capacity were derived. The solutions are given in terms of Gauss hypergeometric function, and it depends on shape parameters and average signal-to-noise ratios of both main and wiretap channels. To gain more insight, we derived high signal-to-noise ratio approximations for two critical practical scenarios. First, the wiretap dominating case where the eavesdropper has the average signal-to-noise ratio much higher than in the main link, and the main channel dominating case where the main channel has much higher signal-to-noise ratio. We derive these approximations for both symmetric and asymmetric channel conditions. In the symmetric channel condition, in the symmetric case, the fading parameters for both channels are equal, which physically corresponds to practically important scenario when the eavesdropper and the legitimate receiver are closely spaced within some small coverage area of the transmitter. To validate our derivations and analyze the performance, numerical simulation with the setup given in the table was performed. First, we performed a comparison of the results obtained with the Lomax model with the classical fading models. Here we have solid lines corresponding to the closed form solution, empty markers to numerical simulation, and cross markers to Monte Carlo simulation. It is clear that our results give quite a good match with Monte Carlo simulation, validating our theory. The analysis of the results demonstrate that when the main channel has the signal-to-noise ratio advantage, the Lomax model consistently, it is this region, the Lomax model consistently provides the worst secrecy performance among all the assumed models. For example, to achieve a given probability of a strictly positive secrecy capacity, the Lomax channel requires a significantly larger signal-to-noise ratio advantage for Bob than in case of a classical Rayleigh or Nakagami M channel. Here we can see this penalty. This plot quantifies the secrecy penalty of operating in a full hyper-Rayleigh regime. The only channel that comes close is Nakagami M with M smaller than 1, which also represents severe fading conditions. Now let us turn to the physical layer security analysis, particularly for the Lomax fading channel under a specific fixed set of conditions. For a wiretap channel, it is on the left plot, and the destination channel, it is on the right plot. Here we have blue dashed lines which present the derived asymptotics for eavesdroppers dominating case in the left plot and for the channel dominating case in the right plot. One can see that the derived results present only the upper and the lower bounds on the secrecy performance correspondingly. Moreover, the bound in the eavesdropper dominating case is quite tight, whereas in the main channel dominating scenario it is quite rather loose. To study the impact of the channel parameters, further results will be given in terms of joint contour maps, starting with the joint impact of Lomax parameter alpha in the both which are symmetrical in both channels. We see a strong dependence on both values of alpha D for the destination channel, main channel, and alpha E for the eavesdropper or wiretap channel. Here we have symmetric in signal-to-noise ratio case in the left plot and asymmetric on the right plot. One can see that the dependence on alpha is highly nonlinear. Thus, we can conclude that when both channels are statistically similar, for example, when we have the same alpha in the main channel and the eavesdropper channel, weak and are quite weak, so we have the values of alpha somewhere around 1. The system is highly vulnerable, and even small changes in eavesdropper's channel has a dramatic effect. Here we see these effects. On the strictly positive, the probability of strictly positive secrecy capacity. And our results help to quantify this secrecy loss. Employing the increased signal-to-noise ratio in the direct channel, here we have on the second plot an advantage of 10 dB for the main channel. The impact of Eve's channel parameter alpha is greatly diminished. This demonstrates an important insight that a strong power advantage in the legitimate receiver can effectively overcome the detrimental effects of a statistically powerful eavesdropper in a severe fading environment. Lastly, let us perform the joint analysis depending on the average signal-to-noise ratios in both channels. For the symmetric cases, here we have both plots for the symmetric cases. Here, the diagonal line acts as a sharp divider between the regions with a high, it is on the top, and the low on the bottom secrecy. The quantitative analysis helps us to establish the signal-to-noise ratio gain that is required to achieve the given secrecy. To increase, for example, to increase the probability of strictly positive secrecy capacity from 0.1 to 0.5, Bob needs a signal-to-noise ratio advantage of about 13.8 dB. For the most severe case of alpha equal to 1.01, and for less severe hyper-Rayleigh fading with alpha equal to 10, this requires those requirements are reduced to about 10 dB. So the gain is about 4 dB. This clearly shows that the heavier fading, the fading, the more costly is to achieve the basic level of secrecy. Summarizing the above and concluding the performed analysis, I'd like to give some closing general remarks. First, the research presents a closed-form solution for the probability of strictly positive secrecy capacity and secrecy outage probability in case of full hyper-Rayleigh fading represented with a Lomax fading channel model. Second, the high signal-to-noise ratio asymptotic expressions are obtained for two distinct cases, the symmetric and asymmetric cases, and for two fading scenarios, the wiretap dominated and the main channel dominated cases. All the results are verified with a numerical simulation and Monte Carlo simulation. Third, the performed numerical analysis provides a critical lower bounds for secrecy performance essential for robust design of secure future wireless systems. I must point out that our research can be of specific interest for wireless communication systems where physical layer security is required, but which are highly susceptible to severe fading and shadowing. For example, urban microcells and millimeter wave links, industrial IoT, and smart factories. Thank you for your attention. I'll be glad to answer your questions.
Alexei, somebody from the audience, questions? No? Well, Alexei, I have some comments and some questions. It is very interesting that in both papers you are using somehow heavy tail fading distributions. And in both cases, we see that these heavy tail fading conditions restrict a lot of, make a heavy restriction on the systems, right? Because here you need for secrecy, you need a very strong signal to noise ratio.
Yeah.
So the question is here, in your previous paper, I thought that the heavy tail condition was imposed on the free space optical channel and the turbulence was there. And here I see that, this condition of free space optical channel is not there. But anyway, we have a heavy tail fading conditions. So if the question makes sense, I would like you to explain a little bit more where these heavy tail fading conditions actually come from. Because when we have a classical Rayleigh fading, we know that it is line of sight or no line of sight component, and that's it. So here, where it comes physically, the heavy tail fading conditions?
This is quite an interesting question because those models are generally derived statistically from the given experimental data. So, for example, when you have such conditions like smart factories or industrial Internet of Things, or, for example, vehicular to everything communications, so when you have no line of sight conditions or sometimes even shadow line of sight, heavily impaired line of sight, the fading that such channels exhibit can be and usually are much heavier than predicted by the classical Rayleigh model. So this idea of introducing heavy fading regimes, and the main idea of those papers was to use the heavy fading, hyper Rayleigh fading conditions, because they can help to quantify this idea. So in order to quantify the heaviness of fading, we use those three metrics: the ergodic capacity, the outage probability, and the amount of fading. And the idea of using those distributions, here we have like Lomax model, and in the previous research, in the previous presentation, it was the inverse power Lomax model, was that those models introduced quite recently, indeed, they are not derived from physical perspectives, or rather they are derived from statistical perspectives describing the existing reality, existing fading envelopes in real life systems. And the strong point of those models basically that they can help to assess closed form solutions, because, for example, there are numerous models like Hoyt model, like second order statistical description model, like second order Rayleigh fading or Rayleigh fading, which which do not allow to obtain any quantitative results in closed form due to their complexity, high complexity. And the presented models which we use in our research nowadays are quite easy to implement, not only analytically but in hardware, because the computations are quite easy, and at the same time they nicely describe the existing quite severe fading in like urban communications.
Very interesting research, Alexei. Thank you very much. No questions, people, audience, no? Well, Alexei.
Thank you very much.
Большое спасибо.
Спасибо вам большое.
Увидимся в следующий год.
Спасибо большое. До свидания.
Gracias. Gracias a todos.